In this video, we will look at chapter 4 of David Albert's book Time and Chance. And chapter 4 is called The Reversibility Objections and the Past Hypothesis. Now, we are finally going to get, at least in sort of the main lines, Albert's story about how to understand and explain the thermodynamic asymmetry that we see in the world. But let's return to where we left off last time. So Albert left off at the end of chapter 3, having explained the second law of statistical mechanics, which roughly says something like this. If your system right now is in a high entropy state, then it is very likely sometime in the future to still be in a high entropy state. Whereas if your system right now is in a low entropy state, then it is very likely that sometime in the future it will have evolved into a high entropy state. So high stays high, low becomes high, and it seems that we got that just from thinking about, in a very abstract way, the laws of physics, and then we added this sort of statistical postulate, which basically tells us that we can think of systems as evolving kind of randomly in phase space. And because we have seen from the laws of physics that there are certain areas of phase space that are much bigger than others, right? Certain macro conditions. There are many more ways to get certain macro conditions than to get other macro conditions. And big macro conditions in phase space have by definition high entropy. And so if we evolve randomly through phase space, we are going to spend most of our time in those big macro conditions, those high entropy states. And if we are there right now, we'll probably stay there. If we are in a very small, very low entropy state and we move randomly, we're probably going to move out of it into one of these really big macro states. And so from just thinking about the probability of random movement on the one hand and a basic insight into how macro states and the laws of physics kind of work together, we get time asymmetry. I explained in the last video why that can't be true, and that is exactly what Albert is going to explain in the first part of this chapter as well. So this can't be true, right? It can't be true that if you take some laws of nature which are symmetric in time, and you take a sort of statistical idea which has nothing to do with time at all, right? There's no idea of time in the concept of probability. You can't take two things that are symmetric in time, put them together, and get something that is asymmetric in time, that is different towards the future than it is towards the past. So either the conclusion that we drew at the end of chapter 3 must be wrong, the high entropy stays in high entropy, low entropy goes to high entropy, either that must be wrong, or it must be true, but not asymmetric in time. Which of those two is the case? It is the second. What we said about probabilities and entropy is, in a way, exactly right, but it's not asymmetric in time. Okay. I explained that using somebody walking away from the Eiffel Tower or walking towards the Eiffel Tower, and I'll come back to a thought experiment more or less like that in a second to explain most of the things that Albert is doing in chapter 4. But first look at those two objections that Albert talks about, because they are physically interesting and played an important role in the philosophy of statistical mechanics and the history of thinking about statistical mechanics. So one set of objections are reversibility objections, where basically what you do is this. You say, well, take some system in a low entropy state that has evolved to a high entropy state, right? So there's a bunch of particles, maybe they're all on one side of a container, there's a gas all on one side of a container, you let it evolve for a while, and all the particles end up sort of dispersed throughout the gas. Now, take that high entropy state and flip all the velocities of all the particles. And then look what happens. Well, it's all going to move backwards, right? I mean, that's what happens because the laws of nature are symmetric in time, or at least the laws of Newton are symmetric in time. So it's all going to move backwards, and all those particles are going to move back into this one part of the container that they started out in. And so for every sort of possible situation of the system where it moves from low entropy to high entropy, there's gonna be this other state where it moves from a time-reversed version of the high entropy state to a time-reversed version of the low entropy state. And because, we are thinking at this moment about the distribution of particles across this container. If you change all the speeds, the distribution across the container isn't changing. So in this high entropy state, which is high entropy because the particles are everywhere in the container, if I change all the velocities, it's still high entropy. This low entropy state where they're all in one part of the container, if I flip around the velocities, they're still in that part of the container because I'm not changing the positions. So it's still a low entropy state. So this time reversed process is a process where a high entropy system becomes a low entropy system. And for every possibility of the system to go from low entropy to high entropy, there is this time reversed possibility where they go from high entropy to low entropy. And so we haven't found a time asymmetry, right? I mean, if one thing occurs, then the other thing must be able to occur as well. And at least in sort of physical phase space, it's gonna look like there are exactly as many low to high trajectories as there are high to low trajectories. And this does not at all contradict the claim that typically, like with high probability, high entropy states remain high entropy states and low entropy states become high entropy states, right? Because there's a very, very few low entropy states compared to the high entropy states. So there's this small bunch of low entropy states and they become high entropy states, sure. And then among all this vast number of high entropy states, there's a small number of them, like as many as there are low entropy states, that are going to turn into low entropy states. And that's also perfectly all right. And so this is fine, right? I mean, suppose that you have a country with 1 billion people where every year at random one person is chosen to be king. It is very likely that the person who is king this year is not going to be king next year. And it's very likely that a person who is not king this year is also not going to be king next year. But that's not an asymmetry in time, right? It's just an asymmetry because there are very few kings, only one, and a lot of non-kings, all the others. And so that's what you get. The king is very likely to turn into a non-king, but any non-king is very unlikely to turn into a king, even though there's going to be exactly as many kings turning into non-kings as non-kings turning into kings at the next lottery, namely one. Right? One king will become a non-king and one non-king will become a king. So you get these probability statements, but they're not actually pointing at a time asymmetry. All right. Here's the second kind of objection. There is in statistical physics something called Liouville's theorem, which is basically based, like the proof is based on the idea that if I have a bunch of states in phase space, like some little volume, then as it moves through state space, it's going to stay exactly the same size. Can't get smaller, can't get bigger. So this set of states that I start out sort of thinking about, it's going to move through phase space. And it can't possibly sort of somewhere in the middle return to itself, because then you would have two trajectories that are different becoming the same trajectory, which is impossible in these under these deterministic laws of nature. So this phase space thingammy is going to move, and it might change shape, but it's not going to change volume. It moves and moves through phase space. And if the phase space is finite, that's an important thing. If the phase space is finite, but if there's, for instance, finite energy and only a finite volume, then you're going to have a finite phase space. If it is finite, then at some point, it's going to have to come back to where it was, right? It's going to fill up phase space. Maybe it doesn't fill it up completely, but it fills up at least some part of it. But it can't go on filling up parts of it because at some point it has to run out of room and it has to sort of return to that initial state and then follow the entire sequence again. And so we have something like we have this theorem which tells us that for any deterministic system with a finite phase space, any state that you start out in is gonna get not back to that very same state necessarily, but as close as you want. Right? No matter how close you want to get back to that original state, you're gonna get there. So if the world as we know it is a purely statistically mechanical Newtonian system, like it's deterministic, phase space remains the same at all times. I mean, that might not be true, right? If the universe is expanding or something like, I mean, there's a lot of reasons to think that it might not be true. But if we have a finite universe, just Newtonian mechanics, then necessarily there's gonna be a point in time at which we are doing this again, right? As close to this, right? Me talking into the camera, you watching the video, as close to that as you desire. That's gonna happen again. And in fact, and parenthetically, Nietzsche knew about this probably, and it might have been one of the inspirations for his thought of eternal recurrence. Those scholars are they have very different ideas about whether he was really inspired by physics or not. I mean, that's a debated point. So, if that's right, if every system is going to go back to where it started after some unimaginably long stretch of time usually, well, there can't be any asymmetry where we always go from low to high entropy, right? Because apparently, if we start out with low entropy and go to high entropy, if we wait long enough, we're going to get back to low entropy again. And that also is true. I mean, that also is something that is just the case in statistical mechanics with some assumptions. And again, this does not actually contradict the conclusions that we had at the end of chapter 3, that high entropy states are likely at a given point in the future to still be in high entropy, and low entropy states are likely at some point in the future to have gone to high entropy, because the system is just going to spend a lot less time in the low entropy states. And so for any random point of time you choose, it is extremely likely to be in high entropy. Just as this country of 1 billion people, if they are immortal, right? They are immortal, they live forever. Every one of them probably is going to be king, even infinitely many times. But at any given point of time, a person is very unlikely to be king, right? There's only a 1 in a billion chance. And that's what the world kind of looks like. So, yes, it's going to return to those low entropy states. It's going to become king again. But that's going to happen very rarely. So rarely that you basically don't see high entropy states going back to low entropy states. Okay, so what are we to do about this? Right? Because now it seems that statistical mechanics is not in the end time symmetric. There can't be a time asymmetric version of the law of entropy. Right? If we have a good story about it, it actually ought to be time symmetric. Well, what is that good version going to look like? Right? How are we going to understand the thermodynamic or statistical mechanic behavior of the world once we have seen that it can't be time asymmetric, at least not if we have only the laws of nature and some thoughts about probability? Well, I'd like to return to my Eiffel Tower Paris thought experiment, but, let's talk about birds. The nice thing about birds is that they can fly, so I don't have to worry about, buildings standing in somebody's way or rivers standing into somebody's way or something like that. Suppose that there are on the world billions of birds. I mean, that's probably true. But also these birds are flying totally at random. Right? They're just, I mean, all of them are flying at random. Fairly fast, but at random. In any direction, they can change direction at any moment. They're just taking random paths through space over the globe of the world. Now, let's take a bunch of birds that are right now at the Eiffel Tower. And let's wind forward time by, let's say, an hour. If we choose the speed of the birds in the correct way, then this is going to be true. Almost all of the birds who are now at the Eiffel Tower, like 1 hour from now, they're going to be in the greater Paris region. But they're no longer going to be at the Eiffel Tower, but they're going to be in the greater Paris region, right? They're going to be in Paris. All right, so most of the birds starting out at the Eiffel Tower 1 hour from now are going to end up in Paris. And if we move forward time a little bit more, those same birds are going to end up somewhere in the world that's not Paris, right? If we take some moment of time sufficiently far into the future, almost all of the birds which are moving randomly are going to have left Paris, right? They're somewhere else. Maybe they're in Burundi, maybe they're in Antarctica, maybe they're in New York, who knows? But they're going to be, like most of them are going to be somewhere else, spread out over the globe. So we've got this bunch of birds which are right now at the Eiffel Tower, and almost all of them are going to move first to Paris and then to the rest of the world. And if we take a bunch of birds in the rest of the world, right, they're not in Paris and not at the Eiffel Tower, they're in the rest of the world, and we speed up time, or we move forward through time, most of them are still going to be in the rest of the world, right? A few might have flown into Paris, maybe 1 or 2 are at the Eiffel Tower, but that's very rare, right? Most of them are in the rest of the world. And this exact same story is true if we look at the other way in time, right? If we look at the past, if we take this bunch of birds at the Eiffel Tower and we ask, well, where were they an hour ago? Very, very few of them will have been at the Eiffel Tower. Almost all of them will have been in Paris. And if we go back even more and we say, well, where were they yesterday? Then almost all of them are going to have been in the rest of the world, right? Not in Paris, but in the rest of the world. So we get the exact same truth about the future and about the past, which is that almost all the birds in this low entropy state, the Eiffel Tower, it's small, right? A small part of space. That's why I call it a low entropy state. Almost all of the birds in this low entropy state used to be in a higher entropy state and are going to move towards a higher entropy state. Okay. Now, the way I set things up, the Eiffel Tower is the lowest entropy state, so birds at the Eiffel Tower can't actually go any lower, right? So let's look at a bunch of birds that are right now in Paris, but not at the Eiffel Tower. So we look at a bunch of birds that are now in Paris, let's say all the birds that are now in Paris, but not at the Eiffel Tower. Where are they going to be like a day from now? Well, most of them are going to be in the rest of the world, right? Very few of them will still be in Paris, and even fewer will be at the Eiffel Tower. Most of them are going to end up being in the rest of the world. What about the birds that are right now in Paris like a couple of hours ago? Well, maybe 1 or 2 were at the Eiffel Tower, but probably most of them were in the rest of the world. Right? So if we look at the birds that are now in Paris, almost all of them came from the rest of the world, are now in Paris, and are going to go to the rest of the world. So if Paris is our medium entropy state, and the Eiffel Tower our low entropy state, and the rest of the world our high entropy state, then the birds in the medium entropy state are very likely to move towards high entropy and are very likely to come from high entropy. And those birds in the middle entropy state are very, very likely to not go towards the low entropy state of the Eiffel Tower, and are also very likely to not have come from the low entropy state, the Eiffel Tower. So what we are seeing, and this is basically what statistical mechanics tells us is likely, what we are seeing is that given a system that is in a non-maximum entropy state, right? So it's not in high entropy, it's somewhere below high entropy. It is extremely likely that that system will move towards high entropy in the future, and that it comes from high entropy in the past, and therefore that we are currently at an entropy minimum. For any system, statistical mechanics tells us that it's very likely, I mean, if we make the assumption that the systems right now are sort of, it's random, right? We don't have any other, there's no reason, and in fact there's no fact about the world that makes it the case that these are like special systems, like specially selected systems. No. If we just sort of assume a kind of randomness of where these systems are coming from and where they're going to, then for any system, it is extremely probable that it is right now at an entropy minimum, and that both in the future and in the past it was in higher entropy than it is now. Clearly, this is time symmetric, and this is basically the story that statistical mechanics tells us. And now we are in real trouble again, because this doesn't seem to be the world as we know it. So take, for instance, a glass which contains some water and a half molten, half melted, whatever, a half molten piece of ice. So a glass of water, a half molten piece of ice in it. Where is that going? Well, first of all, we can think of this glass as being a sort of medium entropy. There's a more high entropy state, which is it melts and everything becomes a uniform temperature. And there's a more low entropy state in which, like, the ice cube is bigger and the water is warmer. Right? The ice cube could be very big and the water could be boiling hot. I mean, that would be a lot more, a very high entropy state compared to the current, very low entropy state compared to the current one. So, given that we have just seen that statistical mechanics tells us that our system is probably going to high entropy and coming from high entropy, this is what we should conclude. Very likely, towards the future, this half ice cube is going to melt, and the entire glass of water is going to become of uniform temperature. And the history of the system is very, very probably that it used to be a glass of water at uniform temperature, and spontaneously it turned into a glass which contains half an ice cube, while the rest of the water became warmer. So we should expect half ice cubes to melt toward the future and to have spontaneously appeared from water in the past. We absolutely should not expect this half ice cube to have been a whole ice cube 10 minutes ago. I mean, that is an extremely low entropy state. Very unlikely that our system came from there. And this doesn't make any sense. It makes sense, but it doesn't make any sense as a description of the world. If I show you a glass with some half molten ice cubes in it, you absolutely do not think that they spontaneously formed from a colder glass of water. In fact, you understandably and correctly conclude that I put some whole ice cubes into this glass and they've been slowly melting. But that is completely against what the laws of statistical mechanics are telling us. So, that's why I said we are in trouble. Right? The idea that we are currently at an entropy minimum, because that's what the law of statistical mechanics seem to tell us, doesn't fit at all the observation that we seem to be in a period of increasing entropy. Right? If we look at the past, in all these, all these examples where gases are expanding and things are mixing and so on and so forth, in all of the examples, we seem to be moving from low to high entropy. But according to statistical mechanics, what should be the case is that we are moving from high back to high entropy, being at a local dip. So how to deal with that? Well, Albert is going to tell us, this is his solution, and it's the second part of the title of the chapter, it's the past hypothesis. He's going to tell us that we should be more careful about our statistical postulates, so to speak. Because we shouldn't claim, for instance, about those ice cubes, that they are completely randomly distributed. That any distribution of particles in the world forming an ice cube, that is a half an ice cube and a medium lukewarm glass of water, is equally likely. In fact, what we know, because of what we know about the past, is that this glass is very likely to be in an exceptional state. Namely, this very exceptional state where the past was even more low entropy than the present. Right? And that doesn't just hold for ice cubes, it holds more or less in general. It seems that our world is in an extremely exceptional state. Namely one where the past had lower entropy than the future, even though almost always to have the current macro state of the universe would be ways where the past had higher entropy than the present, just like the future is going to have higher entropy than the present. So we seem to be in an extremely extraordinary state. And in order to sort of make use of that information, we have to say that our, statistical postulate tells us that the world is sort of randomly distributed over all the things, over all the states that are compatible with, and then we put in some truth about the past. But which past? Right? If we put in a truth about 10 minutes ago, we say, 10 minutes ago the world had lower entropy than the world has now. And since then, statistical mechanics has been at work, entropy has been increasing, that's great. But then if we look at more than 10 minutes ago, we're going to have the entropy of the world also increasing. And that's not how we think the past looked. Right? We think that the past looked like a continuous entropy increase. So if we put like our postulate, like the world was in a low entropy state a year ago, or 10 years ago, or 100 years ago, or 1,000 years ago, that's just going to postpone the problem, because as soon as we go before that moment, we're going to have to say that presumably entropy was higher before that moment than it was after that moment. And we don't want to say that, right? We want to go lower and lower and lower entropy as we work towards the past, because that's what fits our observations, right? And so the only thing that we can really do, Albert says, is we take the beginning of time. Right? We take the Big Bang, or whatever the beginning of time may be, and we say, well, that was an extremely low entropy state. And so if we want to do statistical mechanics in such a way that we get the real world out of it, we need three ingredients. We need the past hypothesis, which says that at the beginning of the universe was in an extremely low entropy state. We take the laws of nature, which are time symmetric, and we take these ideas about probability, which basically tell us that we should act as if the world was a randomly chosen system compatible with this past hypothesis, namely that we started out with extremely low entropy. Those three ingredients are going to give us the correct story, which is the story that entropy has been increasing. Without the past hypothesis, we don't get that. Right? Without the past hypothesis, we get the claim that we are currently at an entropy minimum, and that is not the story that we want. Okay, let's think a little bit more about why that's not the story that we want. What is wrong with saying that, in the past, the entropy was a lot higher than it's now? Well, the problem with that is that it contradicts our records and memories and so on. Right? It contradicts your memory that you have seen these ice cubes melting in glasses of water. I mean, that has never happened. If we just take statistical mechanics without the past hypothesis, then that has never happened. In fact, basically everything you remember has never happened, and all the photographs and records and books and stories that people have been telling us and so on must be wrong. But here's what statistical mechanics tells us. Statistical mechanics tells us that it is much more likely for something like a memory of a low entropy state, or a record of a low entropy state of any form whatsoever. It is much more likely for such a thing to randomly fluctuate from high entropy and thus be false, than for there to really have been a low entropy state that generated this record. So if we take statistical mechanics seriously without the past hypothesis, we get the bizarre situation that we should conclude, or it seems that we should conclude, that nothing that we remember about the past is true, that the past was not as we think it was, the past was a high entropy state, there never were any ice cubes, maybe, in fact, come to think of it, there never were any half ice cubes either. I mean, I seem to remember that, but it's much more likely that my memory fluctuated out of high entropy without there ever having been any of those ice cubes, because those ice cubes are so unlikely. So, in effect, what we get, and Albert doesn't talk about it in this chapter, though he might later in the book, I'm not certain, maybe in chapter 6, what we get is the following claim, that if statistical mechanics is our only guide to the world, what we should really believe is that we are a Boltzmann brain. And a Boltzmann brain is a brain that sort of, the universe is in an extremely high energy state, high entropy state. Everything is just sort of, the gas is all dispersed and whatever. It's a little bit more subtle with gravity, but okay, so there's a lot of this like entropic chaos, so to speak. And sometimes, very unlikely, but it happens, sometimes a brain just spontaneously comes together out of all this matter with some memories about a past that was low entropy, and then it disperses again. That is a very unlikely occurrence, but it is much more likely than there to have been an entire Earth with its history and so on. And so it is extremely likely that you are a Boltzmann brain, having just fluctuated out of entropic chaos for a couple of seconds to think these thoughts, ironically, and then you'll disappear again. And that's it. That's what the world is most likely to be like. And nobody really wants to believe that, I suppose, but in fact it kind of makes a mockery of itself, right? If you are just a Boltzmann brain fluctuating into existence for a couple of seconds, then I suppose you don't actually have any reason to believe that you are a Boltzmann brain, because you didn't ever get any evidence or think through thermodynamics or whatever. I mean, none of that ever happened. So this theory is sort of, it's a skepticism that, like so many skepticisms, is self-defeating. But it's not so clear to see what we should say about it. What Albert says about it is, well, we can just assume the past hypothesis. And to a certain extent, that's right. But I don't think he has given us a very good reason in this chapter to... he doesn't really explain why we should believe the past hypothesis. I mean, and that seems important, right? Why should we believe the past hypothesis? And Albert tells us at some point that he thinks, we should inductively believe it because it helps us to predict certain things. But I don't think that move works. Because if the past hypothesis is false, right? If we are not in this weird low entropy, sort of too high entropy state of the universe, a stage of the universe, if the past hypothesis is false, then, I'm just a Boltzmann brain or something like that. And none of those predictions ever happened. So without the past hypothesis, it seems that we can't even take the predictions seriously that the past hypothesis has made possible. And so I'm not seeing how we could sort of get out of that bend or bind just by postulating the past hypothesis. It doesn't seem to give us a reason to believe that it's true. I mean, why not believe that we're a Boltzmann brain? Given that whether there has ever been any evidence that got accounted for by the past hypothesis depends on the truth of the past hypothesis itself. If that hadn't been true, then either the evidence wouldn't have been there at all, or the evidence is much more likely to just come from a random fluctuation too, and not from a real low entropy past. So I'm not certain. No, I am certain that we did not hear enough about that yet. And Albert is going to talk about knowledge and action more in chapter 6, but there are some big unanswered questions here that we definitely need to be asking. So that's one problem. I mean, why believe the past hypothesis? If we have it, we might deal with some issues, but even whether there are issues is going to depend on whether we have the past hypothesis or not. So there's a fair part of the chapter where Albert discusses some alternative solutions to the reversibility objections. And I'm not going to go into that. I don't have a lot to add. I mean, it's definitely true that people have tried to solve this time asymmetry problem in ways that don't make a lot of sense if you think them through. And so the past hypothesis at least has the positive thing about it is that I think it actually works to introduce an asymmetry. Right? If you postulate this low entropy past, then it works to generate an asymmetry. But of course, I mean, there's a big price to pay, which is that a low entropy past seems more or less by definition to be extremely unlikely. Right? Because that's what a low entropy is. It's an extremely small part of phase space, and so one's first idea would be that it's very unlikely to take place. Of course, it's only unlikely to take place if we have some reason to believe that all possible beginning states of the universe are equally likely, and we don't actually have that, maybe. And so maybe we can't say anything about the probability that the past hypothesis is true. And we are in a weird epistemic situation where many of our most basic tools of assessing whether we should believe something or not just don't work. We will think more about that as we move through the book, for instance, into the chapter about knowledge and action. But for now, what we have seen is that thermodynamics and statistical mechanics do not by themselves at all solve the problem of time asymmetry. That trying to solve it through the past hypothesis is certainly a nice try, certainly something worth thinking about. But there's a lot of difficulties that come with that solution too, and we'll need to think about them more. Thanks.